Okay, so let's start very briefly to talk about the equilibrium in 2D. Previously talked about in 2D, very quick. In the 2D, I said if you have an object that is subjected to some forces, and some moments, it doesn't need to have a moment, but if you subject it to some moment, I have an equilibrium that says we have to satisfy two equations. But first, all the forces applied on that should be zero, so we make sure that it doesn't cancel, it doesn't move to the left, right, or up and down. And also we have to make sure all the moment, all zero, make sure that it's not rotating, it's not spinning in its place. We didn't have the second one for the particle, because the particle, yes, when it's not, there's no moment on that, there's no spin. But here it can spin and it can move. So similar to what we have, if you want to solve any problem for equilibrium, we have to have the free body diagram of that. So same as before, when we want to draw a free body diagram, the first step is that we just remove all the forces and support from that object, like it's suspended in the air, it's isolated uh, in the air. So the first step is just remove all forces and moments and supports from object. Other word, isolate that object. The second one, the second step, we will put all the forces that wants to move the object, all the forces or moment that wants to move the object, or they call it the active force. So second, so here also moment. So apply all force and moment that wants to move or spin the object. Here's they're called the active force. So put all the active force and moment on that. The third step, put all the forces that wants to hold it in a place. And we want to do that. How we do that? Remember, previously we want to do that here. We replace all supports. So we're gonna, if you have a support, you're gonna replace all support with the reaction that wants to hold the object in place. So we replace all support with reactions that want to hold object in place. So the first two steps we did it for the, it's very similar to what we had for the particle or the point. But when it's come to 2D, the supports are a little bit different. So we want to look at it to see how we are gonna work with that. support. So the next step is that, okay, if I have a support, how I remove that support and replace it with a reaction. So, want to see what are the supports, reaction. In the book, if you look at page 198 and 199, it has a couple of the supports. We're not going to use all of them, but I'm going to just mention the one that we are using them the most and say how to replace them. The first one that we are going to use a lot is the roller. So, the example of the roller,
it looks like it's just payment access. I guess I don't really. Oh wait, is that like a grocery cart? Like it has wheels.
so wheels. This example of rollers is so if you have a car, the tire support this car in its place. So your car doesn't fall off on the ground. So
Yeah.
those wheels or the tires, they behave like a. So I can say, okay, if this is a car, there is. So there's gonna be the wheels there that hold it in a place. So the. So those wheels will behave as a. So I can go ahead and replace that. So if I only look at the car, I can go ahead and say, okay. And then replace them with the two forces that hold it in place. So what is specific about the what I call this A and B, call it AY and BY, or R at A or R at R at A, R at B. So what's specific about the roller for the car if the brake is not involved?
It rolls, at least it's able to.
Rolls. So that still does it let it to go down?
No.
So the roller is that it doesn't let you to move in one direction, but it lets you to move in another direction, like the wheel. If you have the cart, it lets you to move it back and forth, but it doesn't let you to push it down. So here is like that. This roller doesn't let the car goes up or down. Doesn't let it go down, but it doesn't prevent it from moving left or right. In other words, the roller only constrains the motion of the object in one direction. It can't do anything else. Also, I can hold the front of the car and roll it. Like the motorbike, when you bring the front wheel up. So that wheel doesn't prevent you to bring it up. So it only doesn't let you to go in one direction. How usually is represent in the book or somewhere, usually is represent like this. So it's a triangle with the line beneath.
And that means roller?
It means roller. So if they zoom in, sometimes when they have the zoom in, they put the roller between these two lines. They put some small circle there. But usually it's like that. So this is equal, if I call it this, for example.
So is that small line underneath the triangle supposed to represent like the ground, basically?
No, it's like, it's two plates. It's two plates that there is a ball ring between them, so
Yeah.
you can
Okay.
move on top of each other. So you're representing this with R in the Y direction. So we replace that with a single force, with a single reaction. Remember that Ry is, or the R at that point is always perpendicular to the roller. It doesn't need to be horizontal, it can be, have any angle. So if it has an angle, it's always perpendicular to that angle. The next one is the pin. Can I give you an example for the pin?
Well, there seems to be different types of pins. There's a smooth pin slash hinge, or there is the roller or pin in a confined smooth slot.
Okay. Let's make it easy. So if I have that, and let's call it point A. See something?
Yeah.
So if you have that, about point A, that point A doesn't let it to go to the left or right. It doesn't even let it go up and down, but it lets it spin, right? So that's the pin. Roller only restricted the motion in one direction. The pin restricts the motion in two directions. So when I have that, if I want to replace it, I will go there, here, at point A, and then I will have this. So I'm gonna have two forces there, so it's gonna be R at A, R at A in the Y direction, R at A in the X direction. So why I replace it with two? Because I want to make sure it doesn't move to the left or right, or doesn't it go up or up and down. How does it represent it? It's represented with a single triangle, no line beneath it. And it's going to be equal to, when I want to, this is going to be 1 Ry and 1 Rx to prevent them from their motion. The direction I'm just using the positive direction. You can use any direction and then calculate it. To see if the direction you got is right or wrong. So, if you have a triangle without anything beneath that, it's a pin. The third one is the fixed. The fixed support. One of the, for example, good example for that. Usually, not always, but usually if you have a home, and then you have the balcony on that home. The balcony that you have, about point A, So that balcony doesn't go left or right. It doesn't go up and down. It doesn't spin. Correct? So it doesn't go left or right. It doesn't go up and down. It doesn't spin. So I can go and only keep the balcony here and say, okay, if I want to have that, I should have one RA in the Y direction, RA in the X direction, and I should have the M and A that prevented it from the rotation. So how it's usually shown? It's usually shown like this, so something like that. So it's usually shown like this, and then again when we want to the Pearson tree, put the tree. So R Y, R X, and M. So these three are probably the most important one. One other one is the rope. If I have a rope, it's more something like that, and the rope over there. You can replace the rope with the tension in the rope. So remember, the rope is always in tension and always in the direction of the rope. So if this angle is theta, this angle is going to be also theta. The next one is the smooth contact. But if you have the smooth contact, so if I have something like that and a smoothly contact with that, so I can replace the or so if I go ahead and I want to replace that with the 4, so that's going to be checked. This is going to be the line of that, line of this. And then it's going to be normal to that. We get R. It's going to be normal to the surface, so that's going to be there are a couple of more there in the book, you can look at it, but mostly, in majority of time, we only use the first 3 So this part is that when I said that replace the support with the reaction here, this is what I would do. So I have a support. If I have a pin, replace it with a single force normal to the pin. Sorry, the roller. If I have a pin, replace it with two reaction. If I have a fixed, replace it with two reaction and one moment. So that's the third part that I touched here. Replace the support with the reaction. So this is the part here. Question? There are 2 points. I'm going to mention it. Why not use them? But the first one is that internal force, they do not have any effect on equilibrium in general. So internal forces do not have effect on so internal forces, as long as they're internal, you don't care if it is problem solving. You are not going to be worried about it. Later on, we will talk about that we split the object in half. In that case, the internal becomes external, so we have to consider it. But as long as they are internal, we don't need to be worried about them. And the second is that the weight of the object, if you are told that the object has a weight, the weight should be put on the center of gravity. So, weight of object be considered or should be applied at the center of y at center of gravity. Totally not considered. So later on, we will get to the point that's okay, how we can calculate the center of gravity, but usually before that we are given that's the center of the gravity. Any question? a couple of examples. So if I have a beam like this, and 100 Newton meter from here. So if I have that and it is 100 kilogram, so if I want to draw a free body diagram for that, so this is going to be equal to free body diagram for that. The first step, just isolate the object. So the object I have is the beam. So I will isolate the object. So that's my object. The next step is I'm going to put all the forces that want to move that object. So I have 1200 here. What else wants to move it? The weight. The weight is going to be at the center of gravity. So for this simple object, it's going to be right in the very center. So if I consider that, that's also going to be the weight, which is 100 times 9.81. So that's the G. Any other forces wants to move it? So now I have to put the forces that wants to hold it in place, or in other words, I have to use the reaction. So what I have is the fixed reaction at the left. So to replace that fixed reaction, so I'm going to have to put these three there. If we'll call it A. So if I call that point A, so I have three reactions there. I have AX, make sure it's not going left or right. I have AY, make sure it's not going up and down. And I have M to make sure it's not spinning at that point again. Remember that the direction that I choose, I just choose it assumed. When you do the calculation, you might find out that the direction is wrong. If you calculate it and it comes negative, it means that the direction I assume was wrong. But you just assume it. I just assume it as a positive x, positive y. But this one means that this doesn't let it to go left or right, this doesn't let it to go up and down, this doesn't let it twist. Got it? So the next one, assume we have the you might have something like this, and there is a so again, if I want to, let's move 300 to okay, if I want to draw the free body diagrams, equals that. Isolate the object, so the object I have. forces that wants to move it are, the only force I have here wants to move it is the weight. There's no other forces wants to move it, so it's gonna be the W, which would be 300 times 9.81. The forces that want to hold it in this place, so one is gonna be there, one is gonna be there. So I'm gonna have 1R, let's name it. So if I could simply call it A and B, I call here A, here B. So I have 1R at the A, normal, and I have 1R at the B. Normal. That's how it's gonna hold it. So next one, assume I have, let's just assume I have a box for it then. That is connected to a pin at that point, A. And with the rope is connected to so with the rope is connected to there, that point. And so for example it's 200 kilograms. Again, if I want to draw the three-body diagram for that box, say first of all isolate it, so we'll just draw the box itself. Then all the forces that wants to move it. In this case here, it's only the weight. So the weight is going to be at this. So that's the weight, which would be 200 times 9.81. The forces that wants to hold it in place, so A is a pin. So I have to make sure it doesn't go left or right, it doesn't go up and down. I don't care if it can spin. So I will put one here to make sure it's not going left or right, call it AX. I want to put one force here to make sure it's not going up or down, I call it AY. So that's what I have at the A. At point B, I have a rope. Rope is always in tension in direction of the rope. So I'm going to have a T there also. So again, if that angle here is whatever, if it is theta, this is going to be theta. So when I have my free body diagram like here or here or here, then whatever analyzing those sigma fx is equal to 0 and sigma m equal to 0, I will write it for this one, for the free body diagram, not for the original. So I use those equilibrium equations and I have them in this form. Understand? So when I have them in this shape, in free body diagram format, I want to write the equation of the equilibrium. So then I have it like this. I want to write the equilibrium equation. So I write it at the beginning of the class as a vector. But let's look at it to see how easier that I can work with them. The equations of equilibrium. The first form that you can write the equation of equilibrium is that I want to make sure it's not going anywhere in the x direction. So sigma fx should be 0. I want to make sure that it's not going anywhere in the y direction as well. So sigma f y is 0. Also, I want to make sure that it is not rotating, it doesn't spin. So I have to go and find the sigma about point O with 0. So that is the first form sets up equilibrium equation in the 2D. For any object that I have, this is what I have to use. That is one way. That's the probably the most common way that we are going to use it. But we are not specifically bound to that. I can go ahead and replace any of these two with the moment as well. So what I mean that I can go ahead and write that sigma fx would be 0. And then I will go ahead and say sigma m about a point A should be 0. And I said the sigma m about point B should be 0. I can also use those three equations rather than the first two. The only thing is that I have to make sure AB is not parallel with the Y. That's the only condition that I have to make sure. It has the AB should not be parallel with the Y. I can do it with the similar, instead of that, I can say sigma. I can write it this sigma Fy is 0. And then replace sigma Fx with the moment. Sigma m 0. Sigma m about point B is 0. Again, the only condition is that AB should not be parallel to X. Or I can go ahead and replace all three of both Fx and Fy with the moment. I can go ahead and say sigma m about point A0, sigma m about point B0, sigma m about point C0. What's the condition? A, B, and C should not be on the same. So A, B, and C should not be on the same line. So I should not be able to pass the line through ABC. So again, that's the most common way that we're using. This is one. When they said write the equilibrium equation, this is the one. Probably 90% of the time, this is the one that we use. But I won't say that we are not born to that. Sometimes it's easier to replace one of these two or the other, or both of them with the moment. So, couple of points here. First, we don't need to use it in this order. We need to use it like that. Usually, if we choose the right order, we don't end up to solve the three equations triangle. If we don't use it in the right format, we end up three equations triangle. We have to solve the system of equation. But if we know that if we use them in an order that each of them give us one equation, usually we don't end up there. So you don't need to write it exactly. You may find that if I write sigma Fy first, it's only one unknown there. So I write it and find that unknown. Then you see, if I write this one, again this one has one unknown. Then you do that and then you do that. So you can using it in any order that you want. So use the order of equation that's easier to solve. And you will see sometimes when you try to problem, I might start with the moment, or I might then start with sigma Fy. So just use it in the order that's easier to solve the problem. This point O here can be any point. The point O here can be any point. Any point on the object or off the object. Okay? The only point is that use the point that most of the force pass through it. Okay? So for moment, for sigma m, O can be any point. So try to use a point that most forces pass through that. Why try to use a point that most of the force pass through it? Because if the force pass through the point, the moment would be zero. So you don't need to calculate momentum for those forces. But the point that point O, again, can be any point. On the object or off the object, anywhere. In other words, it should not spin about any point. It's not that it should not spin about a specific point. It should not spin about any possible point. Otherwise, it's not in equilibrium. Listen. So let's look at one example. So if I have beam like that,
What page are you on, Professor?
210, and there's going to be what's that point here, which is 600 newton. There's going to be 100 newton here. There's 200 newton here. Oh, I don't have to use the board. Two, meter. Okay, if I have that, I want to find the reaction of the force, reaction of the supports. So, first of all, I have to draw the free body diagram of that. then all the forces that I have, this is 45.
All the active forces.
All the active forces. So it's gonna be 600 there. 45. Then I have 200 here. I have 100 here. So these are the forces that active, and then I need to have all the reaction forces. So the reaction here, I have a pin at point A, so it's going to be AY. And here, I'm going to have two of them. Let's see if here it is. It's going to be the B, Y, Bx. I just choose it, the Bx that follow the book. You can't choose it, you can use it the other direction. It doesn't matter. You use it to the left or to the right. So that's the point A, that's the point B. So I want to find it, the sigma fx, sigma fy. So I have to go and find all the components of the force. So this one is 600 sine 45. This one is 600 cosine 45. And again, this is 1, 2. This is 2, 3, 2. So, if I start with sigma fx is 0, how many unknown I'm gonna get? If I write it sigma f is 0, I'm gonna get only one unknown. What about sigma fy if I start with sigma fy? I'm gonna get 2. So sigma fy is probably that I don't want to use it as ARP. I want to push it as much back as possible. So I will start with sigma fx. Sigma fx is 0. The forces that I have is 600 cosine 45 positive minus bx is 0. So the bx would be 600 cosine 45 or 424. It's positive, it means that the direction I chose is right. Now that I have the bx, again, if I write the sigma fy, ay is unknown, by is also unknown. So I will end up with 2 unknowns in one equation. So I'm not going to use the sigma y equal to 0. Instead, I'm going to use the sigma m 0. Which point do you think is better to write the sigma m 0 about that? I can write it about any point. It just make it easier or harder. There's no right or wrong. Any point you choose is correct.
B.
So, if I do it about here, I have, because I don't want to end up with 2 unknown in the equation. So either I have to write it about the A to make sure I get rid of A, or I have to write it about B to make sure I get rid of B. So at B, there are 3 forces pass through the B. So I'm writing at the B, so make sure I don't need to calculate the moment for these 3 forces. So I will write it about the B. 0, counterclockwise positive. So if I write it, I start from the left, here and go. So that I have 100 times 2, counterclockwise, so it's positive. Here I have 600 sine 45. The distance is 5. Again, counterclockwise. So so positive. This one is 600 cosine 45 minus 0.2. So 600 cosine 45 0.2 clockwise. Negative. And then I have the AY times 2327. And again, the AY is going to be clockwise, so it's going to be negative 0, right? So in that equation, only AY is unknown. So I can go ahead and say, okay, the AY would be if I write the equation correctly, it should come out as 319 Newton. Right? So now I already exhausted the sigma fx and sigma m. I have two options. Either write the sigma m, sigma fy 0, or write the sigma m about another. Sigma fy or sigma moment about another. If I look at it, if I write the sigma fy equals 0, I have only one unknown. So probably easier to write the sigma fy 0. So I will go ahead and say, now sigma fy is 0. So the forces that I have, I'm just going from there. So I have the AY minus 600 sine 45 minus 100 minus 200 plus BY is 0. So I already know the AY from there. So if I put the AY there, the only unknown would be BY, which would be 405. Again, you could have used any other orders or equation. Just make it easier or harder. It's not wrong or right. By practice, you learn that which equation you use first is easier to solve the problem. So, the object, then the free body diagram, then sigma fx, sigma fy, sigma m0 in the order that makes it easier to solve.